Hello, my name is CHUN from KGSEA Math Circle, and today in this video, I'll be covering basic number theory concepts. It's an introductory lecture, so I'll not go too deep into it, but it'll help you familiarize yourself with the basic concepts that you could widely see in many competitions. So the first concept we'll go over is what's called the mod. So let's first define what mod or modulo is. As seen here, it's shown as the three-line equal symbol, and it's said that x is congruent to y modulo m. And x is congruent to y when their remainders divided by m are the same. It's also equivalent to saying that m is a divisor of x minus y, or x equals y plus km for some integer k. So here are some examples. You could say that 1 and 5 are congruent mod 2. This is because their remainders when divided by 2 are the same, since they're both odd numbers. Another example would be that 17 and -4 are congruent mod 3. And note that negative numbers can also be used here in a mod statement, as you see here. So now let's take a dive into modular arithmetic. There are two principles that we'll go over. Firstly, it's that if A and C are congruent modulo m, and B and D are congruent modulo m, then firstly, you could say that A plus B and C plus D are also congruent, and that AB and CD are congruent. So there's the addition and the multiplication. So let's prove this. First, for the addition, we'll rearrange A plus B minus C plus D as A minus C plus B minus D. And you can see that the first term, A minus C, is divisible by M, and so is B minus D. So the addition of two multiples of M is also a multiple of M. And so by the definition of mod, we can conclude that A plus B and C plus D are congruent. Now for the multiplication proof, we can set A and B as xm plus C and ym plus D for some integers x, y, and k. Then after calculating AB using this substitution that we just did, we can find out that AB is km plus CD. And from the definition earlier, we could conclude that AB and CD are congruent modulo m. So let's figure out how this new tool can be useful in a problem. Say that we're given 3x and 11 are congruent modulo 4, and we want to figure out what the remainder when x is divided by 4. So first, using the multiplication arithmetic rule, we could write 3 as -1, because those two numbers are congruent mod 4. Then we can multiply -1 to both sides, once again using the multiplication rule. And then finally, we can add 12, which is congruent to 0 mod 4, to get that x is congruent to 1 mod 4. In other words, when x is divided by 4, the remainder is 1. And now let's find out about multiplicative inverses. It's a bit harder concept, so don't feel too discouraged if you find this difficult. So first, the definition. If xy is congruent to 1 modulo m, then y is a multiplicative inverse of x modulo m. This means that by multiplying a multiplicative inverse on both sides in a modular equation, you can simplify one side by making the coefficient into 1. So the really important part of this concept is this theory. For any x coprime to m, its multiplicative inverse modulo m exists. So here's how the proof goes. Consider a set S where S equals 0x, 1x, 2x, 3x, ... and minus 1x. Now, a special property of this set S is that all elements of it are distinct modulo m. Now, we can prove this point simply by contradiction. So suppose AX and BX are two elements inside the set that are modulo m, congruent to modulo m. Then by definition, m is a divisor of a minus b times x. And this means that m divides a minus b. But due to a and b's range, a cannot equal to b, which means this is a contradiction. So now that we have that S's elements are all distinct mod m proven, since an m element S has elements with all distinct modulo m, by the pigeonhole principle, there must exist one element that is 0 modulo m. Now, for convenience, we can call that element yx equals 0 mod m. And as such, we prove that for any x coprime to m, its multiplicative inverse, y mod m exists. So before moving on to the next concept, let's first solve some problems. Now, this is from AMC, 2006 AMC 10B number 11, and I'll give you some time to read the question. Okay, so now the key to this problem is to find the summation modulo 100. And one thing to note that is 10 factorial is 0 modulo 100, because simply it's a multiple of 100. And so the next thing we could figure out is that then every n factorial where n is greater than 10 or equal to 10 are also multiples of 100, since they're all multiples of 10 factorial. And that means the summation we want to figure out is congruent to 7 factorial plus 8 factorial plus 9 factorial. And after calculating, we can figure out that yields 40 modulo 100. And since we're wanting to find the tens digit, the answer would be C. Okay, so now let's solve 2021 Fall AMC 12A number 10. I'll give you some time to read the question. Okay, so the first step of the problem would be to express the number given into more familiar terms. Now, let's first change the base 9 here to base 10. Now let's use our modular multiplication rule to change the 9s into negative 1s, like this. And then this is much easier to deal with because negative 1 to some exponent is much easier to calculate. And after some simple calculations here, we could simply get that the answer is D. Okay, now 2010 Amy 1 number 2. Although it's an Amy question, I find that it's not that difficult, so try giving it a shot. Okay, so we want to find the product of this modulo 1,000 since it's asking for the remainder of that. So this question is also solvable using our modulo multiplication rule. So note that 999, 9,999, and so on are all just simply negative 1 modulo 1,000. So thus the product equals 9 times 99 times a bunch of negative 1s. And to be exact, that would be 997 negative 1s because there's total of 999 terms, and excluding the first two, there would be 997 negative 1s. So we could calculate this simply into negative 891. And then after adding 1,000, we can get that the remainder is 109. Okay, so our next concept is about divisors. Firstly, we'll figure out a method on how to acquire the number of divisors a number has, which is easily solvable using prime factorization. And note that by saying divisors, we're only considering the positive ones. So say we want to find the number of divisors of 12. So first we would prime factorize it into 2 squared times 3 to the power of 1. And then after adding 1 to each exponent of each prime divisor, and then multiply them together, we get the number of divisors we have, which is in this case 6. So why does this work? Well, divisors all look like 2 to the power of a times 3 to the power of b, where a equals 0, 1, or 2, and B equals 0 or 1. So A has 3 possible selections, while B has 2 possible selections. And thus, by multiplying this, we can get that there are 6 divisors of 12. Now, we can apply this knowledge to solve problems such as this. I'll give you some time to read the question. Okay, so note A, B are positive divisors of 30. So our motivation would be to find the number of divisors of 30. And using the method before, we can get that there are 8 divisors because after prime factorization and then adding 1 to each exponent and then multiplying that, we get 8. Thus, there are 8 possible A values. And then B would be autofilled, meaning if A is decided, then B is automatically decided. Thus, there would be 8 A comma B solutions. Okay, so now let's solve a competition problem here, which is 2020 Amy 2, number 1. Okay, so this is quite similar to the question before, except the fact that m is squared. And this changes the constraints a bit. Because if we try to prime factorize 20 to the power of 20, which equals 2 to the power of 40 times 5 to the power of 20, we can't directly think that the number of divisors of 20 to the power of 20 is the answer. Because, for example, let's say n equals 20 to the power of 19. That leaves m squared equals 20 to the power of 1, which obviously does not work because m has to be an irrational number. So m has to have a tighter constraint. So the direction we need to take is to figure out that m must be a divisor of 20 to the power of 10, or 2 to the power of 20 times 5 to the power of 10. And only that way does it satisfy that m squared is a divisor of 20 to the power of 20, while n can be automatically decided. Thus, the answer is the number of positive divisors of 20 to the power of 10, which is, from our method before, 21 times 11 equals 231 pairs. And this is our answer. So this concludes the basic concepts in number theory. We went over modulo, modulo arithmetic, and multiplicative inverses, as well as divisors. And I hope this video helps you with your further studies and competition performances. Thank you.